So this video looks at differentiating growth functions. So y equals a to the power of x is a growth function when a is greater than 1. So for example, we've got three different curves shown here. We've got y equals 2 to the power of x in red, y equals 3 to the power of x in blue, and y equals 4 to the power of x in pink. Now, when x equals 0, you can see that all three of these growth functions go through 0, 1 on the y-axis. And that's because, if you remember from your rules of indices, anything to the power of 0 equals 1. And then, if x equals 1, then our value, our image, is going to be its base. So you can see that y equals 2 to the power of x goes through 1, 2, y equals 3 to the power of x goes through 1, 3, and y equals 4 to the power of x goes through 1, 4. So let's investigate the gradient for the function y equals a to the power of x by considering y equals 2 to the power of x. So firstly, we can see that as x increases, the image y also increases. And the gradient also increases as x gets larger. You can see the gradient gets steeper along our y equals 2 to the power of x curve. So if we want to plot the graph of the gradient function, in other words, dy by dx, then we can look at each of those integer values and the gradient at those points and plot them onto a new curve. And you can see that y equals 2 to the power of x looks very similar to dy by dx of y equals 2 to the power of x. However, if we consider 2 points at the same x value on each of our curves, on our y equals 2 to the power of x curve, at x equals 3, y equals 8. However, on the graph of the gradient function at x equals 3, dy by dx is approximately 5.5. So let's plot the two graphs on the same axes, and you can see that our gradient function is below our y equals 2 to the power of x function, and it's approximately 0.69 times 2 to the power of x. So what do you think will happen if we repeat the process for y equals 3 to the power of x? It's going to go up more steeply than y equals 2 to the power of x. So we're going to get a similar result, but the gradient function is now going to be above the curve. So we can show that y equals 3 to the power of x is approximately 1.1 times 3 to the power of x. And you can see that I've demonstrated that here, showing the two curves side by side. So when we've got y equals 2 to the power of x, you can see that our gradient function is below. However, when we've got y equals 3 to the power of x, our gradient function is above. So it suggests that there's a value somewhere between 2 and 3 where the gradient of y equals a to the power of x is equal to a to the power of x. So the value of a where the gradient of y equals a to the power of x equals a to the power of x is an irrational number known as Eulers' number. And we know that Euler's number is 2.71828182845 and so on. Now you've encountered irrational numbers before because pi being 3.142 and so on was also an irrational number. Now John Napier used Euler's number as the base of natural logarithmic functions. And if we raise e to a power, it's known as our natural exponential function. So at every point on y equals e to the x, the gradient equals y. So if y equals the natural exponential function e to the x, then its gradient dy by dx will be equal to the exponential function. Note that if a does not equal e, then the derivative of a to the x with respect to x is not equal to a to the x.